Well, let's discuss partially out now. My wife has been complaining that when I finish the videos, I say, see you in the next video, and I should say something funny. To be honest, I have no clue what to say. I know I'm gonna try something different on this video, but she's has been complaining that, you know, I sound like super boring. Anyway, I'm super boring, so I don't understand. Anyway, I'm being authentic. So in any case, welcome to our last video in this unit about partially out. Here, what we're going to do is we're going to decompose the variables x1 and x2 and into their orthogonal components, and I'm going to show you that actually the regressions, the coefficients will be identical. So this is important to understand exactly why and what OLS is doing. So what regression does, and what OLS is doing all the time, is separating things and doing decompositions. So if you remember, when we were doing the analysis on the single variable, when y equals, let's say, you know, alpha plus beta x plus epsilon, what the regression did was to take the variable y and separate it in two parts. One was the y hat, the predicted value. The other one was e epsilon hat, the residual. This is the part that has the beta hat, okay? This is the part that has the epsilon hat. I'm just restating. And we know that we prove that actually what OLS does is that it's going to make this component here to be orthogonal to this component. In other words, the covariance between the x's and the residuals will be zero in such a way that we know that the residuals and the predicted values are going to be zero. So that decomposition happens all the time. And in fact, the multivariate is the same expression, but it's going to be among all the elements, not only about the x and the residuals, but all the elements. So this is going to find a way to get all these orthogonal components and analyze the impact of each variable independently on the objective. Well, in this case, the y. Okay, so this is a procedure that I would like to just state and show you more or less what happens. So I'm going to take x1 and I'm going to run a regression between x1 and x2. Okay, so I just created some coefficients cx and beta x, and we know that if I run that regression, I'm going to have two aspects. That x1 will be decomposed into parts. It's going to be on the predicted part and on the residual part, okay? And we know that because, you know, when you run regression, this is what you do. This part will be correlated with the x. Is that okay? This part will be orthogonal to the x, meaning that the covariance between x2 and that residual will be 0. So let's write that residual. That residual will be, I'm going to use a different notation and not the epsilon. So I'm going to construct a residual, which is the x1 minus the fitted value. This is the fitted value, okay? And then on the third step, I'm going to run a regression, which is just y on the residual part. Notice I'm not running r on the x1, I'm running r on the orthogonal component of x, okay? Remember, rx1 is orthogonal to x2, okay? We know that because Rx1 is this guy, and the predicted value has x2, okay? So they have to be orthogonal. And in fact, I'm going to compare that beta s from this exercise and the multivariate regression where we put all the coefficients, okay? Let me just show you more or less what happens, okay? So again, let me just summarize this example that we had from the previous video. I'm going to state the results and then show you a little bit of the graphs. When we omitted the z, this was a coefficient, we get a bias of 0.78. When we actually have both regressors in the regression, then we recover correctly 0.95, okay, and 5. Now, when we do the exercise of residualizing, which is what I said, is that I take x1, x, and I run a regression with respect to z, okay? And then I take the residual of that regression, Rx equals to x minus the alpha hat minus the beta hat c. When I run the regression with this guy, it gives you the same coefficient. Actually, it's numerically identical. And if you revisualize both, you get the exact same coefficient and standard errors. And you're going to learn about t-statistics on the next unit. So this is the original data. When you take and compute a new x, which is a residual of x, okay? This is how the graph looks like. By the way, the black line there is a estimation. So you see, what you do is that the residual now is going to be uncorrelated with the z. Notice that the green and the red dots are uncorrelated with the z. In the first graph, the z, which are the greens, you can clearly see where the data is. In the second graph, the y continues to be correlated with the z, but the x is not. I mean, because this x part here are the residuals of x on z. And therefore the x's now are equally spread. And when you actually look at that, the two slopes are identical, and then you get the right slope. And that's how you estimate correctly. Why I'm doing this? So the one question you should ask, does R does this for us automatically? Absolutely, that's exactly what it's doing. I'm explaining this because that's exactly what the regression is doing. But why is worth doing it? It's because we want to understand what truly means to control for something. When you want to say what I'm going to control for something, equivalently what you're doing is you take x and you run x on z and all the other variables that you put on the right hand side. So you run x on everybody else. You take the orthogonal component of that, so it's the residual, and the OLS will now run the regression between y and that residual. Okay? Let me do this again. So I have y on x, and then I have a bunch of variables, c1, c2, cn, okay? When the coefficient on the x is the same as running the following procedure. I run first x on all the z's, then I compute the residual, Rx is equal to x minus x hat, and then I run the regression y equal beta Rx. The two betas are identical. That's, by the way, why multicollinearity doesn't work. Because if x and z are perfectly multicollinear, then the residual is identical to 0, and therefore you cannot run the third step. So in this regression, what you're doing is OLS is separating, is stripping out from the x everything that could be explained by the z. And by the way, in the estimation of the z is doing the same. Looks at the estimation of the z and says, let me take everything that is explained by everybody else, take it out, and only use the part that is unexplained. So this is first to understand what it happens. This is second also to understand why multicollinearity fails so dramatically, because there's no residual. And third, this is important because we have many tools that actually what they do in the regression is to run the regression in steps. Runs one regression, then another one and another one. This is called double machine learning. When you do this in a nonlinear fashion, you kind of lose a little perspective of what is happening. And when you do this in a bivariate setting, it becomes very easy. So I guess I will not see you in the next video.